Hello everyone, good afternoon, I should believe. Yeah, so today we're going to start our chapter 1, and then next week, inshallah, we'll do a TD. For in one of our meetings, we'll do a TD, a full TD, and then we can use both days or one day according to it will be according to the amount of questions I managed to organize. But yeah, so next week we'll try to do some exercises, and yeah, we'll move from there. So today we're going to start with our chapter 1, and yeah, we're going to move from here. So should we wait for the others or we start? So
It's that.
we wait.
On commands.
Okay. So the same things apply. You can ask questions. You can unmute your mic to ask questions. So this is the theoretical part of, yeah, and it's very easy, trust me. So you just have to follow me, and yeah, we'll move from there. So
just a question before we start.
Sure.
Yeah, when you say we're going to have TDs, does it mean the TDs are going to start from this chapter, or also including the introduction, the one where we're from?
We're going to include everything. So we're going to do the introduction and part of this chapter. Am I clear?
Loud and clear.
Yeah. Okay. So we're going to start. So we're doing ways.The Coulomb, which is the Coulomb Law. We're going to start from ways.The Coulomb, which is our chapter 1. So we're going to do ways.The Coulomb. So I believe the BCG guys, they do, before they start the ways.The Coulomb, they do a bit introduction on charges. So you're supposed to be familiar with charges. Atoms, we already know that an atom consists of the nucleus, where there's the proton and the neutron, and then we have an electron. And then, yeah, we have charges. We have the proton, which is positively charged, the neutron, which has a charge of 0, and the electron, which is negatively charged. So we're going to do a bit of that, but we're going to start from ways.The Coulomb. So ways.The Coulomb, the Coulomb law is simply, it's a law that helps us calculate the amount of, what can I say, the quantity, the amount of charge passing through a specific area, a given surface, or a given volume. So Coulomb law quantifies the amount of force between two stationary charged particles. So Coulomb law allows us to quantify the amount of force between two stationary charged particles. So it can be positively charged particles, it can be negatively charged particles. So Loi de Coulomb, I'm reading now, so follow. So we got Loi de Coulomb. Soit deux charges ponctuelles Q et Q', distantes et R et au repos. La charge Q exerce sur la charge Q une force F'. La charge Q exerce sur la charge Q' une force F'. So, égal d'après le principe de l'action et de l'action à F the module. So here, simply just trying to explain that if we've got two charges, we've got Q and Q'. Q exists in the direction of Q', and Q' exists, and Q' exists a force in the direction of Q'. So a diagram will illustrate what I'm just saying here. So F is the force that the charge is going to sort of give out. So F is the force. So F is given by the formula F. So the F or the F' is given by the formula 1/4p epsilon 0 and Q' over R squared. So literally, this sort of the expression is coming from this diagram here. This diagram that I have here. So I have the point here. This is a point charge Q, and I have the point charge Q' at the point A and at the point A' respectively. So Q' is going to be exerting a force in this direction, which we've named F', and Q is going to be exerting a force in this direction, which is F. And then the direction of the force has been given the vector U. So the direction of the force is this U here, but as we've seen, Q, the charge Q, it's positively charged. It's exerting a force in the outward direction, and this charge as well is exerting a force in the outward direction, which is this force F' and F respectively. So Q is a charged particle exerting the force F in the U direction, and Q' is a charged particle exerting a force in this direction, which is F'. And then this F is equals to 1/4 pi epsilon 0 multiplied by Q' over R squared. So R squared is the distance from Q to Q'. So R is the distance between the charged particles, which is what we have here, R squared. And then Q' is what we have here in the direction U. And then this is our expression for finding the force exerted by a charged particle. C'est clair? Hello?
I've got a question.
Sure.
Yeah, so like where on the direction of the forces,
Yeah.
like what's causing the forces to move in those directions?
So charges, we have negatively charged particles, right? So the positive charges exert force outwards. So that is what's determining the direction of these forces. So this is a charge, this is a positive charge, and this is the positive charge. The direction is outwards. So it can be in this direction, it can be in this direction, it can be in this direction, as long as it's outwards. Same with this one. Q' is a positively charged, so it's exerting force outwards. So it can be in this direction, can be in this direction, can be in this direction, can be in this direction. Then the negative charged particle exerts force towards the particle. Towards the particle. So the force for the, can you kindly mute your mic? So for the negative charged particle, we'll have the force, but it will be, the direction of the force will be towards the charged particle. C'est clair?
Yeah, it's clear.
Okay. Yes. So we get where this expression is coming from. So we can have F prime or F is the same thing, still the force. So here we're for this one is F prime. So we're calculating this force here exerted by this charged particle Q prime. So if we're trying to find the force exerted by Q, we'll just have F is equals to 1 over 4p epsilon 0, the same thing, over r squared in the direction of U. So U is the vector representing the direction of the force, and r is the distance between Q and Q prime. There are people who, okay, just a minute.
Chawanza,
Yeah,
Chawanza,
yeah.
just a minute. Someone has posted in the group that she's waiting for the invitation.
Oh, okay. I'm sure he's in now. Who that? I think I've invited everyone now, by now. Yeah, so we continue. So are we clear here before we move on?
Wait, what did you say Q and Q prime were?
Q and Q prime are just charges. Like this is a charge, this is a charge. So it can be a positively charged particle or a negatively charged particle. So we've got Q and Q prime representing the charges. So the charge is going to be exerting a force in a certain direction. But I've said a positive charge exerts force outside, not towards the particle, but is outward. And then the negative charged particle exerts force towards the particle. So in this case, we can clearly see that we've got two positively charged because their force is outward. It's in the outward direction. So Q is exerting force in this direction, in the direction of U outwards from the particle, and then the same with Q prime outwards from the particle, which is F prime, the force for Q prime, and we've got F for Q respectively in the direction of U. This is where this expression comes from. So for us to find the force, we have 1 over 4 prime epsilon 0 times Q prime over r squared. And I said r squared is the distance from Q to Q prime. Is it clear?
Yeah, so is there a possibility of having the force negative?
Yeah, there is.
Okay, so does that tell us anything, like the force being negative?
The force being negative, meaning you have a negatively charged particle, I believe, going the outward or inward direction.
Okay.
Yeah. So that's what I have to say about the Coulomb law, which is this here. So we have F with the vector, it has direction. I repeat, it has direction. That's why there's an indication of a vector. So we have F prime is equals to 1 over 4 pi epsilon 0 times this, the modulo of this over r squared. So epsilon 0 is a quantity. And usually they'll give you in the question what epsilon 0 is equal to. Or if you want to know it, epsilon 0 is, it's a quantity of 1 over 36 pi. It's a petty quantity. It's 1 over 36 pi 10 to the power 9. And then, so in case of where you see F is equals to K, Q prime over r squared, don't be alarmed. K is just the representation of all this. So 1 over 4p epsilon 0 can also be represented as Ke, which is the Coulomb's constant. Am I clear?
Yeah.
Okay. Hello?
Yeah, I can hear you.
Yeah, sorry to take you a little bit back, but we had network problems, so we could hardly get what you said after you defined the whole Loi de Coulomb.
Okay, so I should start from after. So I said Coulomb's law.
No, can you please start from the beginning? Because like from the time you sent the link in the group, I pressed on the join thingy, but I wasn't added until some seconds ago.
Okay, so I'll just go through fast. So I said Coulomb's law is a law that helps us quantify the amount of force between two stationary charged particles. And I said if you're doing BCG, you do more on the charged particles where you have an atom, and then at the atom you have a nucleus which has electrons and protons, or electrons and at the nucleus there are protons and neutrons, and then there's an electron running around, and then you're supposed to know that the electron is negatively charged, the proton is positively charged, and the neutron is has a charge of 0. So here we're just talking about charges. So yeah, so the Coulomb's law help us know the amount of force that a certain charge produces. So which is what we're doing here. So we discussed that if we have two charges, from this drawing, if we have two charges, Q and Q prime, which are positively charged charges, and then we know that the force exerted by a positively charged particle is outward, so it goes outward. So it can be going in this direction, can go in this direction, can go in this direction, can go in this direction. As long as it's outward, the direction is outward. The same with Q prime. Q prime is also a positively charged particle because the direction is outwards. So we've got two charged particles, Q and Q prime. The distance between Q and Q prime is R. And then we've got this U just represents the direction of the force. So we've got, for Q, we have F in this direction. And then for Q prime, we have F prime in this direction, respectively. And then our formula for Coulomb's law is this, what I have here. So F, the force F, or F prime is equals to 1 over 4p epsilon 0 times Q prime over R squared. Is it clear? So I also say that here sometimes you can find KE. So instead of putting this whole 1 over 4p epsilon 0, you find K with like a small e. So don't be alarmed, that's just Coulomb's constant. They mean to put this. So it's KE times this, or you find literally just write it out for you, which is 1 over 4p epsilon 0 and this. Is it clear?
Who is
I've got a question.
Sure.
Just there on the direction of forces.
Yeah.
What is the use of A and the A prime?
Oh, A prime is just, we get a point, like how we use in coordinate, the previous introduction that we're doing, we get a point M. So A is just an indication for the place where the Q prime is. So at the point A, we get a charge Q, and at the point A prime, we get the charge Q prime. So that's literally that. So I continue.
I have a question as well.
Sure.
Yeah, the epsilon, does it represent anything, or is there a way that they came up with it?
Yeah, epsilon is usually just tell you epsilon. Epsilon is it's a petite number. It's a really small number. And if you want to know exactly what epsilon is, it's 1 over 36 pi 10 to the power 9. So it's just a representation of a really small number. Yeah, that's epsilon 0, which is 1 over 36 pi 10 to the power 9.
Okay, thank you very much.
You're welcome. So we move, we're saying si, oh my God, okay. So we're saying si le milieu présent entre les deux charges est le vide, et si l'on utilise les unités SI dans ces cas-là. So we have what I'm saying, 1 over 4 p epsilon 0 is equals to this. If you replace here, you replace with your epsilon. which usually in questions, they'll give you the epsilon. So, or they'll give you the KE. So this is KE, which is the Coulomb's constant. So they'll give you this with the SI units. So the SI units for this is Newton meter squared of per Coulomb squared, which they'll give you usually. And then our epsilon is this, which I'm just mentioning. Yes, so we move. So we have Q and Q prime étant le value absolue des charges électriques, Q et Q prime les forces F and F prime respectively. So we have this and this are repulsive if Q and Q prime have the same sign. So as I mentioned, if we have a positively charged particle Q and a negatively charged particle Q prime, oh, and if we have positively charged particles together, they will repel, which is what we're from seeing here, because they will be in, the force will be in the same direction. So yeah, and then this is what this is talking about. Then expression vectorial, we have soit u, le vecteur unitaire de la direction A to A. So we have from A to A, that's our direction u, which is the direction of the force u. So if we're moving from A to A prime, orient the A vers A prime. So we're moving from A to A prime. Vectoriellement, on peut écrire, this is what we have here. So we have F prime is equals to this, this in the direction, this, So yeah, we move I'm sorry, forgive that. So we have CQ et Q sont des mêmes signes. F prime est repulsive. They produce Q prime est allopositive. I think someone is actually asking me about if the force is positive or negative. So we have if the product of Q and Q prime, that would depend on the product of Q and Q prime. So if you have this positive, usually you have your whole force is supposed to be positive. And yeah, so CQ and Q prime sont des signes contraires. F prime est attractive, le produit Q prime est allo negative. So yeah, so we move to the distribution continue the charge density. So most of you ask me, what is charge density? So we have a continuous distribution of density charge. So what is density charge, or what is charge density? So charge density is simply the electric charge per unit length or surface area or volume. So it's electric charge per unit length, surface area or volume. So having told you what charge density is, we can have volume charge density, we can have linear charge density, we can have surface area charge density or surface charge density, which is what we're going to define now. So here we have distribution continue de charge density. So we have densité volumique de charge, which is volume charge density. So we're trying to measure electric charge from a per unit volume, per volume. So we're trying to, for volume, density volume de charge, we're trying to measure electric charge per volume. For surface area per surface area, for linear or length, we're trying to measure it along a certain amount of length. Yeah, so we have density volumique de charge. So si l'on considère un volume de dimension infiniment petit et si ce volume est chargé, on peut considérer que l'électricité est continue. Ainsi, un volume élémentaire dV, so un volume élémentaire dV pris dans un volume chargé V sera considéré comme une charge ponctuelle de valeur dQ. On appelle densité volumique de charge la quantité. So I'm going to explain this. So this passage is simply trying to tell us that if we have, take this is just a representation of a certain amount of volume. So we have V, the whole thing. So we have volume elementaire, which is represented by dV, which is a small volume, a small petit volume from the V. So we call it volume elementaire, which is represented by dV. So we have the whole V here, and then we get a petit volume from the whole thing, which is our dV. And then we're trying to calculate the amount of charge passing through the petit volume. So we have a petit charge or charge. So we have a petit charge, which is dq dv. So for us to have that, we'll have rho. This is not p, this is rho is equals to dq over dv. This is our constant volume density. Volume, what do you call it? Density volumic décharge. So we have rho is equals to dq over dv. Remember in our definition, I said this, we're just simply trying to calculate the amount of electric charge, which is represented by q, but in this case, we have dq because we have petit charge over a certain volume. I don't know if I'm allowed to say amount of volume, but yes, a petit volume, which is dv, which is what we have there. And then unité, so rho se exprimerà in Coulomb per meter cubic. So charge is measured in coulombs. And then we have volume meter cubed. So la charge électrique se exprime in Coulomb, which is, yeah, what I'm saying. La charge électrique is expressed in Coulomb, which is what we have there. So we move la charge totale portée par le volume chargé sera. So from our what do you call it? Our small expression here, which is rho is equals to dq over dv. If we make dq the subject of the formula, we'll have dq is equals to rho dv. Am I clear? So we'll have rho is equals to dq over dv. So if I want to make dq the subject of the formula, I'll just have dq is equals to rho times dv. So la charge totale portée par le volume. So what the charge total carried by the volume is equals to, so if we want to find the charge is equals to 3 integration. So this is just to show us that it's volume. So volume is integrated 3 times. So the dv that we have here, okay, let me take it slow. So we have q is equals to 3 integration of dq. So what have we said our dq is? Our dq is equals to rho times dv. So our dq, if I make dq a separate formula, I'll have rho times dv. So for me to calculate charge, I have charge q is equals to 3 integration volume dq. So I know my dq is equals to rho dv. So if I integrate, rho is a constant. So if I bring the constant outside, I'll have 3 integration of dv, and then which is the same as this. So si rho a constant, the volume est dit uniformément chargé. Alors, we have q is equals to rho by the volume. So if I integrate this, dv, remember it's dv. So for me to have v, I have to integrate it, which is what we're doing here. So the 3 integration symbols shouldn't scare. They're just trying to tell us that we're integrating volume. So volume, we integrate volume, we have v. And then this is a constant. So we move it out. So we have rho, we have this, and then we have dv. So if we integrate dv, we have v, which is what we have here. So if we're trying to calculate charge, and then we have rho, we have our rho, and we have our dv, we simply use this expression or this formula, which is the same as q is equals to rho times v. C'est clair?
Question.
Sure.
What is the significance of integrating 3 times?
They're just trying to show us that we're integrating volume. So there will be integration. So there'll be a lot of integration you see as we move. You get to understand why they used 3 to represent volume. But yes, so the 3 integrations in scale. That's why there's the 3 integration, and then there's a v here. So they're just trying to show us that we're integrating volume. So we move this guy out, we integrate volume, we'll have v. The same thing, just like integrating dv or dx, we'll have x. Integrating dv, we'll have v. But in this case, we have 3 because they're trying to show us that we're trying to integrate volume.
Question.
Sure.
So does that mean that you're supposed to integrate 3 times, or it is just a representation?
It's just a representation.
All right, thank you very much.
You're welcome. So any other questions? Okay, so I move. We have now density surface-seek discharge. So remember I told you there's volume charge density, there's surface charge density, and there's linear charge density. And I explained, so volume, we're trying to calculate the amount of electric charge passing through a certain amount of volume, which we're just from discussing. And then now we're talking about a certain surface area. So we're trying to find the charge, the amount of charge passing through a certain surface area, which is densité surface-seek décharge. So we have si l'on considère une surface chargée, on appelle densité surface-seek ou superficielle. So they will tell you densité surface-seek or superficielle, décharge la quantité. So this is our symbol or representation symbol, like rho. So here we have this, what do they call it? I'll get back to you what they call it, I think of. Yeah, so we have this symbol is equals to dq over ds, ds representing our surface area. So the same explanation, we have S, which is the whole surface area, which is S, and then we get petit amount of that big S, which is ds. And then we know that if we have a small surface area, we know we also have a small amount of discharge to calculate from the area. So we have ds and we have dq. So la charge dq étant portée par un élément de surface ds de la surface chargée. So we have this is expressed in Coulomb per meter squared. If this is a constant, la surface est dit uniformément chargée. So if you have this as a constant, we know that the surface est dit uniformément chargée. And then we know that this is expressed in Coulomb meter squared. So we have densité linéique de charge. This is simply just us trying to find the amount of charges or the electric charge per length. Let me say like along a wire per length. Yes, a certain amount of length. So we have si l'on a des charges réparties sur une ligne, seulement on appelle densité linéique des charges, la quantité. So this is the symbol for linéique. So this is expressed in Coulomb per meter. So this is equals to dq over dl, which, yeah, simply just what we have here. So this is equals to dq over dl. So we have rho is equals to dq over dv. We have this guy here is equals to dq over ds when you're trying to find it along a certain surface area. And then we have this is equals to dq over dl. So am I clear? Okay, we move. Let's shine. Okay, sure.
Yes, sorry for taking you back a bit. There's, you said density surface discharge.
Oui.
I would like to know that symbol which is there. Is it Q with a bar or how
No,
is it?
it's like sure, let me try to remember, see what I wrote in my book. But it's like rho. It's not V with a something on top. It's like, let me try to write it. I hope I manage. So it's something like this. It's something like this, sort of. Can you guys copy that? Yeah.
I see.
A round thing with a, yeah, but you know, people have different writing, so you write it the way you see it. But yeah, it's something like this. It's not a V with a what, it's, yeah, that. So we have 3, le champ electric. So champ is field. So simply that's just electric field. And I'm sure most of us did about electric field in physics. Yeah, so electric field. So now we're talking about electric field. Oui, so le champ électrique, it's le champ électrique in French. So definition. So we place so plaçons at a point M a charge punctuel Q. So at a point M, where's the drawing? So at a point M, we place Q, just like how we did on the first drawing. We had A, at A we had Q. So at M we have Q, celle-ci se trouve soumis à une force électrique F. So nous appelons champ I au point M le cosine. So electric field is simply the force exerted by the particle over the charge. Simply, that's how we get the electric field. So electric field is simply the force exerted by the charge, which is F or F prime, if you're trying to calculate the electric field produced by the charge Q prime. So you have E is equals to F prime over Q prime. If you're trying to find the electric field at the charged particle Q, we'll have F over Q. Oui. So l'unité usuelle du champ électrique est le volt émetteur or Newton per Coulomb. So we have the SI unit is volt émetteur or Newton per Coulomb. Oui, so we have champ électrique créé par une charge punctuelle unique. So this is, we're now trying to simply see the electric field created by a point charge, a unique point charge. So a point charge, it's just like a simple twist of language. So a point charge is a point in space that has an electrical charge. So here trying to calculate the electrical field created by a point charge, a unique point charge. So unique point charge, any point charge. So if we have soit un charge Q placé in A, if we have a charge placed at A, on se propose de trouver le champ I qu'elle crée at a point M. Laissons un M un charge Q prime. Elle soumise à une force V. So this is the force produced by Q prime, as we already know. So avec R is the distance between A and M. So we've got this drawing here. So we've got at A, we have Q. At M, we have Q prime. So we have this force in the direction of U produced by this guy here. And then we have this charge producing this force F prime here at M. So yeah, which is what we have here. So we have R is equal to that, and U is the unit there, the AM. So in the direction, we're moving from A to M, which is, yeah, what we have here. So comme par définition, E champ is equals to F, the force, over the charge, the charge. So we have E is equals to 1 over 4 pi epsilon 0 Q R squared U. So what has happened here is that we have this guy here, which is our force produced by the charged particle here. And then we have our definition of E, of electric field. So where there's F here, you put this guy here. Let me use a spotlight. So where there's F, you put this guy here. So if we put this guy here, we have F divided by Q prime. So if I divide this whole thing by Q prime, you, in your calculations, Q prime and Q prime will cancel. So we'll just be remaining with this. Are there any questions on how we come up with our new expression for electric field? It's not new, where there's F, we put our actual F.
You can just...
Sure.
I have a question.
Sure.
On top of the, below the equation, the one that says with R is equal to M, A, then U, the vector, is equal to, what letter is after the M? Yeah, right there, the one on top.
This one.
No, what letter? U, the vector U is equal to There's a
AM,
fraction there.
AM, the
That's
vector AM over AM. That's how we, it's just a representation of U. So the time tells us that U is the vector that's flowing in the direction of A to M. So we're moving in the direction of A to M, and then that's the fractional representation, so to say. So we have
so they
vector.
won't cancel because there's AM below that.
What?
When they cancel,
No, these are different. This is AM, and then this is the vector AM. They won't cancel.
then where is the other AM coming from, which is not the vector?
AM is just simply the distance from A to M, which is the same as from Q to Q prime. So the distance of A,
Okay.
and this is the vector moving in the direction AM, will give you the unit vector U. So instead of them showing you all this, they just simplified it and just showing you the U, like giving you the U. So you're supposed, okay, not really you're supposed to know, because you know that it will be moving in the direction U, but just for information, you know that U was, we came to accept that U is, you know, the representation of the vector of the direction of the vector and the forces, because we have the vector moving from A to M over the actual distance of AM. That's how we came up with the U vector. So U is goes to AM unit there, the AM. So it's a, yeah. Is it clear?
No. Could you please repeat on how you found this new equation here? I don't know if it's new or it's a combination. Huh?
This equation?
Yes. If you could repeat how it was found.
Sure. So we said we've agreed. Please kindly switch on off your mic. Yeah. So we've agreed that electric charge is simply the force over the charge, which is, yeah, what we did on top there. So we say that electric charge is this, simply F over Q. So now in this scenario here, we're trying to calculate the electric charge produced by Q prime, by this point here, Q prime at M. So what happens is that we have the force produced by the charge Q prime, which is equals to 1 over this times this. We know where this is coming from in the direction U. And then we're told to calculate the electric field, the charge electric. So we have E is equals to the force over the charge. So if we replace where there is F, we put this whole expression here. We put it here, and then we divide it by Q prime. This is simple math. Q prime and the Q prime will cancel. Just do your math if you want to, or when you'll be going through. This Q prime and this Q prime in the equation will cancel, and then you will simply just remain with this. So this is the final expression that we have for charge. Am I clear?
Yes, thank you.
You're welcome.
I have a question.
Sure.
Yes. In the first diagram you gave us, the direction of forces were against each other.
Yeah.
Then on this direction, on
And
this
then this
diagram,
one, they're different.
yeah. Does those do those directions affect the magnitude of the E we are solving for the charge?
Yeah, they do. I feel like they do. So you remember I said that the charge positive, the force is away outwards from the charged particle. So it can be in this direction. Let me just get something. So it can be in this direction, the direction I've indicated, or it can be in this direction, as long as it's outward. It can be in this direction, or it can be in this direction, as long as it's outward. Sorry for that bad drawing. So as long as it's outward, or it can be in this direction. So as long as it's outside, this is a positively charged particle. So that's why we have it, the force moving outward. So now we're just trying to calculate the force they've indicated it moving in this other direction, and I'm sure it will affect the magnitude. That was your question, right? The magnitude of the electric field that we're trying to calculate.
Yes, yes.
Any other questions? Okay, so with the few minutes, we'll continue. So we have, we've talked about electric champ, electric field, yes, in English. So we have electric field, electric created by a system of charges of charge punctual discrete. So if you've noticed in this, where is this? Here we talked about electric charge created by a charge punctual unique. And then now we're talking about, so this is unique is simply any, like, it's just some use of words. It's just any charge, like any unique charge. So we can have Q and Q prime. And then for this guy here, now we're talking about electric field created by a system of charges, the discrete. So these are maybe Q1, Q2, like specified charges. Maybe we have Q1, Q2, Q3, Q4. They've given you maybe the charges Q1, Q2, Q3, Q4 respectively. So for chaque charge, we have QE representing any number. It can be Q1, Q2, Q3. On pair, E is equals to this times this, which is what we're from calculating here. It's just we have charge punctual discrete. It can be, well, now we're finding the electric champ at the charge Q1 or Q2 or Q3 or whatever the case is. So this is what we have. So EI is equals to 1/4 P epsilon 0 QE over RE squared and all that. So we have avec R is equals to the distance from this to M, which I've already talked about, which is R, the distance between this place and the other guy here. So we have this diagram here. We have U is the direction and all that. So we have the charge at A1, charge Q1. They've indicated Q1 at the point A1, and then we have Q2 at the point E2, at the point M. So we have Q2 at the point M. So, no, forgive me. So we have Q1 at the point A1, and then we have Q2 at the point A2, and then we have Q3 at the point A3. So they've given us 3 charges. Let me get my spotlight. So they've given us 3 charges. We have Q1 here at the point A1. We have Q1, we have Q2 at the point A2, and we have Q3 at the point A3. So we have, we're trying to calculate the champ. So we have A from the movement from A to this point here, which is labeled as M. Yeah, so we're moving in this direction. So the vector will move in that direction. We have Q1, we have Q2, and we have Q3. We have U1, U2, and U3. So I want you to notice something here. When they meet at M, we have the electric field produced by Q1 going the outward direction, by Q2 going the inward direction, by E3 going the outward direction. So let me just read and then I'll explain. So we have, where are the notes? Sorry, we have, so let's cast the figure, Q1, Q3 are positively charged and Q2 is negatively charged. So Q1 and Q2 are positively charged and Q1 and Q3 are positively charged. Q2 is negatively charged, which brings me back to this guy. So they're saying Q1 and Q3 are positively charged. Their force and their electric the champ electric is outwards, it's moving outwards. So for Q2 is negatively charged. So the force will be moving towards the charge, and then the champ as well. So which is what we have here. So that's why you're saying this E2 is coming in this direction, the A3 is going that direction, the E1 is moving that direction. So the E2 is moving in this direction simply because Q2 is negative, and we know that forces for negative charged particles are towards, so the champ is in the same direction. We saw what that explains my drawing there. So le champ électrique résultant sera évidemment, so we have this. So if we want to calculate the champ, full champ for Q1, Q2, and Q3, we just do the sum. So I think we've all seen this in math. So this is just the sum, the total. So E can be 4. So we have E, the total of the champ. So we have E1, E2, and E3. This is what this simply means. So we're now trying to get the total champ for all the 3 charges. So when we combine that, we replace with our actual expression, we're going to have E is equals to 1 over 4 P epsilon 0 with the same, what can I say, total expression, and everything follows. So this, do we have any questions to here? Do we have any questions? Okay, so this is our E, our total E for Q1, Q2, Q3. So where there's your E here, first you do up for this guy is telling us that we have to add all of them. So this is a addition, and then this will be our total champ for all the 3 charges. So we move to champ électrique créé par une distribution de continuous discharge. Okay, so what's the time? Okay, 17. Okay, so we end or we continue? Just for 10 minutes, I explain this part.
You can finish.
Okay, so we have we have okay. Sorry. Okay, so we have this. We have champ électrique créé par une distribution continuous of charge. So we have either a continuous distribution of charges or discontinuous distribution of charges along. So if we have any surface, it's either the charges are continuously distributed, which meaning they're close to each other, or discontinuous, meaning one is here or the other one is somewhere else. And yeah, so simply that's what this is trying to say. And then we have distribution volumique décharge. So we have soit un element de volume dV. So we have an element of volume dV centered sur un point A, where the density des charges est rho. Cet element de volume porte les charges dq, such that dq is equals to this, which is what we're from doing. You remember this expression. This expression is originally as rho is equals to dq over dv. So assimilable à une charge ponctuelle. Cette charge élémentaire crée donc un champ à dE donné par l'expression that. So if we have charges, if we have a volume, a certain volume dV, volume élémentaire at a point A where the density of charge is equals to this, set element, the volume porte la charge dq such that dq is equals to this, assimilable à une charge ponctuelle. Yeah, we've read that. So we have dE. So now dE is the champ, electric champ produced by dq over dV. So we have small volume, small charge, small electric. I think this is the simplest way. Small electric champ, electric field. Yes, champ in short. So we have dE is going to be equals to 1 over 4p E0 dq over r squared u. So where there's q here, because our normal expression is supposed to be E is equals to this without the i's, right? Which is this one here. So because we've added, like we're trying to calculate a small amount of electrical field from a small charge, we have dE is equals to, where there's q here, it's not just q, it will be dq, which is what we have here in the direction this, which is equals to this. So we know our expression for dq is equals to rho dv. So literally we're just going to have 1 over 4 epsilon 0 rho dv r squared in the direction u. Okay.
Oui.
Of how I came up with this expression. We're clear with how I came up with this expression.
No, you can try to repeat.
So the E, as I said, dV is, this is the whole volume. So we have a small, we're just concentrating on a small volume, amount of volume, which is, we've named as dV. So we're trying to calculate the electric charge over this dV dq area, small dV dq area. So yes, this is what electric, why am I saying electric charge? It's electric field or charge. Yes. So we have dE is equals to 1, our E originally is equals to this. And we know how we came up with this. We just divided the actual force thing over Q, and then our Q and our Q prime canceled each other. So we had this. This is our actual formula for E. So now at a point charge Q, now we're trying to calculate E at a point charge dQ, a small petit charge. So if we are trying to calculate electric field at dQ, we're going to have dE, small petit charge. So we have dE is equals to 1 over 4, why am I point? dE is equals to 1 over 4p E0 dQ, because we're not finding at Q, we're finding at dQ. So we have dE is equals to 1 over 4p epsilon 0 dQ over r squared u. And then we know our dQ, we're trying to find the electric charge at a distribution volumic discharge. So we know our distribution volumic discharge, we have our expression here as we discussed. Where's our expression? So our expression for our volume, our distribution volumic discharge is this guy. And then when you do up your subject to the formula, we'll have dV. Sorry, we have, which is what we have here. We have dQ is equals to rho dV. So where there's dQ here, you can replace with rho dV, which is what we have here. So where there's dQ, we just simply replaced it with rho dV because we're finding the electric field at a certain volume, given volume. So we used rho dV because we have our expression for calculating the amount of charge at a certain, given a certain volume, which is what we have here, r squared over u. So nothing has changed. What we have is that we're calculating small, the electric field at dq. So where there's dq, we replace with rho dV. Is it clear?
Oui, it's clear.
So we have, this is just a the diagram representation. We have our point A, we have our point M, and then this is our direction of our champ. So our champ will be going outwards, and yeah, so direction from A to M. I'm moving from A to M, so it will be along U, and then our champ will be outwards, and yeah, we have everything there. So I think, yeah, so let me just finish this part. So le champ créé par l'ensemble de la distribution des charges is equals to this. So we have E, as I said, dV, volume. For us to show that we're dealing with volume, they use 3 integrations. So we have E, for us to find E, we have to integrate the E. We all know that. For us to find X, we have to integrate the X. So here we're trying to find E. So we have E is equals to integration of the dE. where we have E is equals to this over this rho dV r squared u. So this is trying to show us that this is the champ produced by a this is a champ from a small amount of volume, dV. So this is what we have here. So the champ, the total champ, not dE, the total champ will have, electric field will be expressed in this form. So this, I repeat, this does not mean that we're supposed to integrate it 3 times, but this is just a representation of us, them trying to tell us we're integrating V. So we have integrating with respect to V, there's V involved, there's volume involved somewhere. So we have, for us to have E, we have to integrate the E. So we have this, so our E is equals to, we have our E here, we've been given our dE, I mean. So if we integrate this guy, this is a constant. We cannot integrate a constant, we all know. So the constant will come on the other side of the integration symbols, and then we'll have dq over r squared, which is what we have here. So I think today we'll end here, and then next week we'll continue. Oh, on Thursday or tomorrow, we'll talk to the lesson, then we'll continue from there. So are there any questions, any queries? And then I said we'll secure a day next week where we'll just do a TD of what we've covered as soon as I get enough questions, or I organize enough questions to answer. And then we'll spare a day for 2 hours, we'll just do a TD, or both days next week. And then we'll just do the TDs, and then we'll move from there. So is that clear?
With a clear.
I just a suggestion, to be better the way we have gone through these notes, the symbols, the calculations, the what, then we even do a TD before having a lot of notes. Then get my point.
Yeah, I get your point, but okay, I get where you're coming from. I think you've done a lot of exercises in analysis, but this module, it's if I gave you a TD based on the introduction, it was just literally just like me giving you a TD on mechanic du power, because literally that was just us just trying to get expressions that we're going to use when we actually start our module. So I didn't want to do that. And then we start our chapter 1, and then yeah, I get your query, but it's hard to organize questions with the TD that I'm trying to organize, or that we're going to have. It's going to be easy because the questions are going to be covering up a lot of, you see why we had to do the first part and this part, like it will be a combination. So I don't know if my answer is what exactly you're looking for, but I get your query. But again, I'm saying I didn't want to give you a TD on just the first part because it was going to be simply mechanic du power, and I'm not really concentrating on the mechanic du power. Right now, we've started doing this. So I'm going to give you questions before we just even finish chapter 1, just the law, the Coulomb, and whatever it involves. And then you're going to see how or why we actually use the first part. And I think that will be best for me. And then we do it together, because usually I'm not usually online, or I don't. Yeah, so we'll do it together, and we'll do it once and for all, and then we move on together.
Point taking.
So I can end the meeting. Everyone is okay?
I think so.
Okay. All right. Have a blessed rest of the evening.